Welcome back, everybody. Thank you for being here. We are going to continue our lightning-fast overview of category theory today. Once again, I just want to say that if you want a more complete treatment of this material, please go check out Emily Reel's book. Category Theory in Context. She does a much better job than I do at presenting all of this information. I'm just trying to get it out there so that I can get it out there. Okay, let's begin first by correcting a definition that I hastily gave last time, and that some of you pointed out was very clearly incorrect, and that is of faithful, full, and fully faithful functors. So, let's take a functor f between categories C and D. So we say that f is, well, three things. First, we say that f is faithful if for every object C and D in C, the associated function of sets, which takes a morphism in C from C to D, to a morphism in D between their images, so this function is injective. Okay, next, f is full if, let me label this dagger, is full if equation dagger, if morphism dagger is surjective, and it is fully faithful if both. So that's cleared up, out of the way. Fully faithful is sort of a good notion of an embedding for a functor. I had said injective on objects and morphisms. That's not a great idea because we don't really want to be thinking of categories as having fixed sets of if we're working only up to equivalence of categories, you can have two categories with wildly different sets of objects, but that are still equivalent categories. Okay, anyway, let's move on to the first major topic of today's lecture, which is the notion of an adjunction. We've seen one sort of inverse for functors, which is the other functor involved in a natural equivalence. In the definition of a natural equivalence, we ended up with, if you remember, we have functors C and D, functors F and G between categories C and D. Ooh, I am really getting ahead of myself there. So an equivalence of categories, we have a functor F, functor G, together with the data of equivalences between the identity of C being equivalent to the composite of G with F, and the identity on D being equivalent to the composite of F with G. Well, in the category of categories. Not all natural transformations are natural equivalences. I apologize for the siren outside if you can hear that. So we can weaken our notion of some sort of inverse to, instead of looking at equivalences here, look at certain potentially non-invertible morphisms. So here's the definition. What I'm going to give is two definitions that are related, and I will leave it up to you to precisely formulate and prove what their relation is. So let's have functors f from C to D and G from D to C. Then an adjunction between f and g consists of a choice of two natural transformations. First of all, a natural transformation eta that goes from the identity on C to the composite G with F. This is called the unit of the adjunction. And a natural transformation epsilon that goes from F composed with G to the identity functor on D. And this is called the co-unit. Making the following triangle diagrams commute. Such that the triangle identities hold. So first we can start with our functor f, and by precomposing with the unit we can get over to f, g, f. And so this is via the natural transformation that I'll call f composed with eta. Then we could also use the unit to sort of the co-unit to contract those first two, f and g. So this is going to be a functor called epsilon circ f, and that will get us back to f. So the first identity is that this commutes, where this diagonal functor is the identity endofunctor, the identity natural transformation on f. And similarly, we can start with g and apply eta composed with g to get to gfg. We can then apply g composed with epsilon to get to g, and that should be the identity as well. Great. So our second definition, if now let me go on to the second definition first. Let's start again in the same way. So let f and g be functors between c and d. F goes from c to d, and g goes from d to c. So we say that F is left adjoint to G, and duly G is right adjoint to F, in both cases written F, then with a turnstile G, where the turnstile points toward F. If there exist if there are natural bijections from Hom in D between f of C and little d, it's in bijection with the set of Homs in C from little c to G of little d. And so these are natural bijections for all little c in C and little d in D. I'll leave it up to you to formulate precisely what naturality means in this setting. It is this latter definition that tends to be most applicable in the real world, knowing that in order to specify a morphism from f of C to D in D is exactly the same datum, as specifying a morphism from little c to G of little d, that can come in handy quite often. It can be a really big help. So the proposition that I will leave up to you to formulate precisely and prove, should you so wish to do so, prove should you so wish. The proposition is that in the setting as above, F is left adjoint to G, G is right adjoint to F, if and only if there exists an adjunction between them. The naturality in these bijections, in particular, you have to have a choice of bijections there, but the naturality of those choices will give you the unit and co-unit identities. The unit and co-unit transformations. Most importantly, let's give some examples of adjunctions, because they show up all over the place. All right. Large class of examples comes from forgetful functors. So let's just start by looking at the forgetful functor from groups to sets. Usually write FGT for forgetful functors. So this forgetful functor admits an adjoint. I can't spell today. It admits a left adjoint. Called the free group functor. It takes a set S to the set of words made up of elements of S or formal symbols called S inverse with a group structure that comes from concatenation. You can find details in many other places. But the idea that there's an adjunction means So let's call this free group F sub S. The free group on the set S is going to be F sub S. It means that to give a group homomorphism from F sub S into any other group G, all you need to do is give a set function from S, not F sub S, S, into the underlying set of G. There are a whole host of free forget adjunctions. In some cases, they're a little bit simpler. The free abelian group functor on a set, for instance, is a lot simpler than the free group. All right, number 2. So the forgetful functor now from topological spaces to set admits both a left and a right adjoint. It admits both adjoints. So we have top and we have set. We have a forgetful functor between them. The left adjoint to the forgetful functor, it takes a set S and maps it to S with the discrete topology. The discrete topology is where all sets are open. The right adjoint takes a set S to the indiscrete topology on S. This is the topology where only S and the empty set are open. This is a great adjunction. A very important one. Okay. Now here's one that I promised you last time. Let F be a ring homomorphism from R to S. Then there is another triple of adjunctions, well, pair of adjunctions, triple of functors. As I hinted at last time. So between L mod R and L mod S, one functor is the restriction functor, called F upper star. That admits both a left and a right adjoint. The left adjoint is the functor called F lower shriek, which is tensoring up. And the right adjoint functor is the functor called F lower star, which was taking the R module of homomorphisms from S into blank. All right. These adjunctions are pretty nice as well. Adjunctions tend to be really conceptually gratifying, in my opinion. It's always fun to notice that you have an adjunction. See example 4. So the inclusion of groupoids into all categories. So this is a fully faithful functor. The inclusion of groupoids into all categories admits both adjoints. So I'm going to write this in the other direction just for my own sake, so that we can have the left adjoint on the top. So the left adjoint, well, let me describe the right adjoint first, because it's a little bit simpler. The right adjoint sends a category C to the category iota 0 C, which is, by definition, the category with objects, those objects of C, and morphisms, all isos in C. So it's a groupoid by construction. The left adjoint to this inclusion takes a category C to what's called its groupoid completion. So this is the groupoid completion. It's analogous to the group completion of a monoid. And what it does is it gives us a category where we formally invert morphisms in C. Non-invertible morphisms in C. So we formally adjoin inverses to all non-invertible morphisms and then take sort of the smallest category generated by those data. Now another fun example, which shows that there are arbitrarily long sequences of adjunctions. So far we've only either seen one adjunction or a pair of adjunctions. And this one I'm taking from Emily Reel's book in her chapter on adjunctions. So let's take some natural number n. For every I between 0 and n plus 1, there is a unique functor called delta I, which goes from brackets n, as you remember is 0 to 1 all the way up to n, considered as a poset category, go mapping to brackets n plus 1, that there's a unique injective, there's a unique faithful functor that misses I. So it's surjective on all objects except for I. Then for each I between 0 and n, there's a unique functor surjective on objects such that I has two preimages. And this functor goes from, it's called S upper I, and it goes from brackets n plus 1 to brackets n. So we end up with a sequence of adjunctions because for each I, now actually greater than 0, strictly greater than 0 and less than or equal to n plus 1, we have that delta I is left adjoint to S upper I minus 1, which in turn is left adjoint to delta I minus 1. And we could keep going. Si minus 2, and so forth. So we have arbitrarily long sequences of adjunctions. There are other places in nature where we may end up with infinite sequences of adjunctions, so not just arbitrarily long finite sequences of adjunctions, but actually infinite ones. Moving on to the next topic, we will talk about limits and colimits. This treatment that I'm giving is not ideal, so I really encourage you to go out and look at some other treatments of limits and colimits. In particular, you'll need to get some practice with them in order to feel comfortable. So limits and colimits are essentially ways to talk about properties that characterize objects almost uniquely. And what do I mean by almost uniquely? I mean uniquely up to unique isomorphism. Going along with the philosophy of category theory, we don't actually want to consider objects that are unique, purely unique, but rather we want to allow them to be unique up to isomorphism, but really we would want there only to be a unique isomorphism between any two such objects with this property. So our first encounter most basic types of limits and colimits. Let's take a category C. An object little c in C is called initial for every C prime in C, there is exactly one map from C to C prime. So there exists one, and there is at most one. Dually, an object D is terminal if for every C prime there is exactly one map from C prime to the terminal object. So, for example, the terminal object in set is the one-point set, and the initial object is the empty set. That there is exactly one map from the empty set to every set, and every set has a unique map to the one-point set. But you might say, well, there are many sets with only one object. True, but there's only one up to unique isomorphism. And so here's the lemma. That gives us our first taste of what uniqueness in category theory really is. if C and C prime are both initial, then there exists a unique isomorphism from C to C prime. And the proof is very straightforward, but also indicative of what to do in other situations. Since C is initial, there exists a unique map from C to C prime. Let's call this F. Since C prime is initial, there exists a unique map from C prime to C. Let's call this G. Again, since C is initial, G composed with F must be equal to the identity on C. And dually, F composed with G must be equal to the identity on C prime. Hence, they are inverse isomorphisms, but they are also the only inverse isomorphisms between C and C prime. Okay. Let's give an example that will help us motivate. Let's just rip the Band-Aid off instead and give the full definition. There are certainly more friendly ways that I could introduce these definitions, but I'm sort of going with what feels best to me at the moment. Mwahahaha, my YouTube channel. All right. Let C and I be categories. And F from I to C a functor. Okay. The limit of F, if it exists, is the terminal datum of an object C in C and a natural transformation from the constant functor at C to F. This is written lim sub I of F, or just lim F when I is understood. What does this mean? Well, it means that for any other, say, little d in C, and natural transformations const d to F, there exists a unique map, phi, from D to C, such that we go from const D to const at C to F, such that that commutes. The dual notion is of a colimit of f. Again, if it exists, limits and colimits need not exist. The colimit of f, if it exists, is the initial datum, datum, potato, potato, of an object C in C, and a natural transformation from F to the constant functor at C. Why did I just dot the O in constant? That was silly. Let's not do that. Okay, and so again, what that ends up meaning is that for all D and C and natural transformations from F to const D, there exists a unique C from C to D where composite const C to const D, the composite const C to const D together with the map from F, where this triangle commutes. And here is const C. Okay. So by abuse of notation, not to be confused with by abusive notation, by abuse of notation, we also use lim f, or respectively colim, to refer to the object, not also its accompanying natural transformation. Let's spell out this definition a little bit more carefully, to be probably more like one that you may have seen or may later encounter in the literature. And we'll do this just for colimits. Limits are dual. So let's have the same scenario as above. We have a functor f from I to C. So then the colimit of f is an object of C equipped with maps from f of little I to the colimit for all I in category I, such that for all phi from I to j in I, the diagram, we go from f of I via phi to f of j, the colimit, such that that diagram commutes. And for any other such C in C with maps from f of little I making the same thing commute, there exists a unique morphism C from, let me give myself a little bit more space. There exists a unique morphism C from the colimit over I of F to C such that this diagram commutes. So that's our C right there, such that that commutes, again, for all morphisms phi in the category I. All right, let's give some examples. All right, example 1. Let S be a set regarded as a category with no non-identity morphisms then limits over S are called products and colimits over S are called coproducts. Now, just to be to clarify, when I say that I'm taking limits over a certain category, I mean a limit of any functor from that category. So a limit over a category S is the limit of any functor from S to some other category. Okay, let's just look at the case of what happens in the category set. In set, products are just Cartesian products. And coproducts are disjoint unions. Let's take I to be the category with 3 objects generated by morphisms like that. This is called the walking cospan. And limits over I are called pullbacks. And so if the image of our diagram is the pullback of the diagram like this is written C cross over F, comma, D, comma, G C prime, or just C crossover D with C prime when the maps F and G are understood. So this is how to compute pullbacks in set. In set, the pullback of a diagram where X maps to Z via F and Y maps to Z via G is, so X crossover Z with Y is going to be the set of ordered pairs the subset of the Cartesian product where f of x equals g of y. Great. Dually, we can take I to be the diagram still with three objects, with the maps going in the opposite directions, so that is the opposite. This is called the walking span. This adjective walking means that a functor out of your diagram is the thing that comes after it. So walking cospan, a functor out of that gives a diagram called a cospan. Similarly, the walking span gives a diagram called a span. So colimits of spans are called pushouts. And these are written x square cup over z y, or whatever. I was thinking about the notation in set, but it could be, c square cup over f comma d comma g c prime. And again, sometimes we don't refer to the maps, and it would be c square cup over d with c prime. And here's how to compute them in set. Push out of the diagram. This diagram, well, it's going to be we're going to take the disjoint union of x and y and quotient out by a certain equivalence relation. And what's that equivalence relation? Well, it's going to say that little x is equivalent to little y if there exists a little z such that x equals f of little z and y equals g of little z. So we're sort of thinking of it as gluing x and y together along images specified by z. Here's an example as well. The category cat has all limits and colimits. In particular, it has products. So C cross D is the category with objects going to be pairs, little c and little d, and morphisms are going to be pairs F and G, where F would go from C to C prime, and G would go from D to D prime. And the pair together gives us a map from C comma D to C prime comma D prime. Okay. Here's an observation. Let C and I be categories. Then C has colimits, has all colimits over I, if and only if the diagonal functor, so functor is sometimes called delta, and what it does is it takes a little c to the constant diagram at C, but only if this diagonal functor admits a left adjoint. And so this left adjoint is going to be called the colimit over I, where you plug in whatever your functor from I to C is. And the dual thing holds for limits. This is the limit over I. And this should be a little bit believable because both colimits and left adjoints are good for mapping out of. And both limits and right adjoints are good for mapping into. Fantastic. Now, these are all examples of a much more general phenomenon, universal constructions known as con-extensions. Their theory is a little bit more than I'd like to get into right now, but let me just give a definition, because it is too enticing not to. So let's have functors F from C to D and G from C to E. Then the left con-extension of F along G if it exists, of course, is the functor written L con sub G of F, and this goes from E to D, together with a natural transformation alpha from F to the composite of L con with G suitably initial. And the initiality is going to be indicated in this diagram. So here is our con-extended functor. Here is our alpha. Here is some other functor, I don't know, what's a good name for a functor? J. No, that's a terrible name for a functor. H together with some random transformation beta, the universal property of the Kahn extension gives us a unique natural transformation here. There is a dual theory of right Kahn extensions as well. Sticking with the concept of only sort of introducing definitions and not really exploring them, let's talk a little bit about monoidal structures. The idea being, we very often come across categories that have some additional operations we can perform on them that don't coincide with any limits and colimits, at least not ones that we have discussed. For instance, we can take the tensor product of abelian groups or rings. We can take the smash product of pointed spaces. Here's just an extremely rough definition of what a monoidal category is. A monoidal category is a triple of a category C, a functor O times, and an object 1 sub C. So of a category C, a functor from C cross C called O times to C, and an object 1 in C called the unit, such that, and here's where I'm going to be waving my hands a little bit. So the tensor product, we call it, is associative, but really only up to specified isomorphism. And the unit object is an identity object for O times, and again, sort of up to specified isomorphism. Some important examples are any category with finite products has a Cartesian monoidal structure. That is C with its product, and where the unit is the terminal object. The terminal object is the empty product. Okay. Another big example. Let R be a commutative ring. Then the operation of O times sub R induces a monoidal structure on the category mod R, and the unit is just the ring R itself. And a final example is that the smash product is monoidal, or rather gives a monoidal structure to the category of pointed topological spaces, and the unit is just the one-point space. Okay, I want to now do a little bit of a bonus for this lecture, and that is to talk about fibrations. This isn't something that you would usually experience in a first 2 lectures on category theory. But it's a topic that will serve us better when we get to the infinity world. So this is sort of preparing us for the infinity categorical world. I also just find it pretty interesting, which is basically the entire reason that I'm mentioning anything in any of these lectures. Definition. Let's take a functor P from a category E to a category B. A morphism phi from E prime to E in E is said to be P Cartesian if there's a specific universal property, if for every psi going from E double prime to E, these E's are the same, so for every map like this in E, and every functor, every map G from P of E double prime to P of E prime in B, such that this diagram commutes P of E double prime to P of E prime to P of E. So this map is P of phi. This map is P of psi. And this map is G. So for those data such that that commutes, there exists a unique gamma. I'm going to draw this now up here. E prime to E. This map is phi. E double prime. This map is psi. So such that with all of that, then there exists a unique gamma from E double prime to E prime, which I'm going to show here. at gamma, making this commute. So the top diagram lies over the bottom diagram via applying P. So this diagram lies in E, and this lies in B. Okay, that is the definition of a p-Cartesian map. A functor P from E to B is called a Grothendieck fibration. Called a Grothendieck fibration. If for any little e in E and any map F from B to P of little e, this is now in B, there exists a p-Cartesian morphism phi from E prime to E such that P of phi equals F. In particular, P of E prime equals little b. We let fib of B denote the category of Grothendieck fibrations over B, where morphisms are commutative triangles. They're commutative triangles lying over B, so E mapping to E prime via F. These both lie over B via their structure maps. P are commutative triangles such that F takes p-Cartesian edges, p-Cartesian maps to p-prime Cartesian ones. Dually, we say that a functor P from E to B is a Grothendieck op fibration This is clunky terminology that ends up being fixed in the infinity categorical setting. The terminology in the ordinary categorical setting is established by category theorists. I deign not to change their view. Okay, so a functor P is a Grothendieck op fibration if the functor from E op to B op is a Grothendieck fibration. And there's a similar similar category called opfib over B. So these are important because they allow us to encode the data of a functor from B to the category of categories, which can sometimes be difficult to construct, as a functor between two categories. That is, as a map inside cat. It's this reduction of category level that is very important. So it tends to be easier to display a functor E to B and check that it is an op fibration or a fibration than to give an entire functor from B into all of cat. I won't make this completely precise, but let me just give part of the construction, which, I'll give part of the construction. Okay, construction. So let's start with a fibration. I'll leave the word Grothendieck understood. And let's pick a morphism in B. Let's define the category E sub A to be the pullback of our fibration P over the inclusion. This is the map that classifies the object A. So that is going to be the definition of our category E sub A. Usually we decorate pullback squares with that little arrow there. Okay, so what we're going to do is we will construct a functor that I'm going to call F upper star from the fiber of E at B to the fiber of E at A as follows. So given an object E in the fiber over B, which an object in the fiber is the data of an object in E together with a map from no, that's not what I want to say. So we'll pick some object of the fiber and we'll choose a p Cartesian morphism phi from E prime to E lying over our map F from up here. And such a p Cartesian morphism exists by the definition of a fibration. The source of this E is unique, so this E prime is unique by definition of p Cartesian morphisms. rather can be shown to be unique by the definition of p-Cartesian morphisms. And so we set f upper star of E to be this E prime. So the action on morphisms, the action of f upper star on morphisms in the fiber over B is also given by, or also follows from the uniqueness in the definition of p-Cartesian morphisms. This functor, the resulting functor f upper star, is called the Cartesian monodromy. Of P over F. So similarly, if P is an op fibration, we can construct a functor I'll call this f lower star. Maybe it should be better called f lower shriek. If somebody knows, please leave a comment. All right, but this goes from the fiber over A to the fiber over B. So we can construct that, called the co-Cartesian monodromy. This terminology comes from, well, something that we'll see soon, which is the action of the fundamental group of a space on the fibers of the covering space. And then the terminology Cartesian and co-Cartesian comes from the Cartesian edges, and then there are also co-Cartesian morphisms. And in the infinity categorical world, we use the word Cartesian fibration instead of Grothendieck fibration, and co-Cartesian fibration instead of op fibration. So these constructions of the co-Cartesian and Cartesian monodromy packaged together, I'll call this an observation. So over all morphisms in B, the Cartesian monodromies packaged together into a sort of into almost a functor, into what's called a pseudofunctor. From B op into cat. And the idea of a pseudofunctor is that composition need not be preserved on the nose, though it will be preserved up to a specified isomorphism, specified natural isomorphism. So the construction, there's actually an equivalence of categories between fibrations over B and pseudofunctors I think it's probably better if I call this something different. Pseudofunctors from B op to cat, and dually there's an equivalence of categories between op fib over B and functors and pseudofunctors, but from B into cat the variance changes. So here is something fun, which is why I wanted to talk about this in the first place in this lecture. So if I have a functor P from a category E to the category brackets 1, remember that brackets 1 has two objects and one non-trivial morphism. So a functor that is both a fibration and an op fibration it induces an adjunction. An adjunction between the fiber over 0 and the fiber over 1. That arrow should go the other direction. Left adjoint there, right adjoint there. Whose left adjoint is Cartesian monodromy. Is co-Cartesian monodromy, and whose right adjoint is Cartesian monodromy. In fact, there is a reverse to this construction. An adjunction induces a bifibration, and the bifibration recovers the original adjunction. I won't go into detail because I actually don't know if the details work in the one categorical world. This ends up being one way of defining an adjunction infinity categorically, that an adjunction by definition just is a bifibration over brackets 1. So thank you for tuning into this lecture. We will get back to studying actual topology in the next lecture, where we talk about what we might want to expect from the category of topological spaces. I hope to see you there. Well, I won't see you. I hope you see not me there. Bye.